Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Let's get started. Let's check out this Tektronix Type 107 square wave generator together. This is from around 1959 or so. I really like the way Tektronix built things way back when, and this has been on my shelf for a while, and I really want to open this up and take a look inside, so I figured I would share that experience with all of you. Now, I haven't done anything to this other than clean the face. So just before this was on the bench here, the face was disgusting. It looked like somebody spilled coffee on this or something. So I got some Windex and just wiped the face down, and it came up pretty nice. And of course the rag was wet, so I kind of just wiped the case off as well. But it came up pretty nice. Still some sticker residue. I don't know if this was a seal, maybe a calibration seal. And on the top side here, there's a little blue dot of some sort for some reason. And another probably cal seal or something down here. But other than that, that's it. Now, I haven't been inside this at all. Haven't looked inside or anything aside from looking through the holes in the side of the case. Again, we'll experience that together. Then what we're going to do is we're going to also take a look at the schematic for this. I'll explain how this thing works, and I'll bring this up slowly on my current limited isolation transformer and variac supply, and we'll see if the thing comes to life and makes some square waves. So we'll make some square waves in style today. All right, what I'm going to do is reposition things here and get the side case off of this. And let's take a look inside and see how they put this thing together. To get inside this early Tektronix equipment was really quite simple. So to get the side off, you just partially loosen these screws. So on the other side is a plastic winged type nut that locks behind the ledge here when you tighten them up, and then when you loosen them, it follows the screw, because the screw drags on it, follows it, and it loosens them off. So very easy to get inside. And I didn't show you the back side here. I'll show you this quickly before I get inside here. So this is where you could just plug a standard extension cord onto if you would like. You can see that the earth is not populated, so they didn't want an earth connection here. Trigger out, and it looks like there's a small fan in behind this grill here, so we'll find that out in just a moment. It does look like some blades in there, doesn't it? I think there is some blades. Yeah, it looks like a small fan in there. So, in order to get this open, in fact, I'll stand this up because they release easier when you have them standing up. So what you do is you just give this just a slight twist like this, and a slight twist like that is all you need, and then the sides just come off. And you can see those plastic wing type nuts. So you can see the little stop here, right? And those just lock behind this little edge right here to hold the sides on. So nice little touch to make these things very easily serviceable. And again, look at this, just a beautiful layout inside. So first of all, that fan is kind of cute. Looks like a bathroom fan style type motor. So really what it is a shaded pole motor, but you see these often in bathroom fans, and you find them in record players and all sorts of microwave ovens and things like that to keep things cool. The reason that they use these is because they're very quiet. And, they provide a, fair amount of power, enough to drive a little blade at any rate. So nice little shaded pole design there. Small core just to move a little teeny fan like this. This little fan reminds me a lot of the fan found in one of the early Gonset 2-meter amplifiers. So any of you ham operators out there might go, hey, yeah, so that looks an awful lot like that little fan to blow on the 826 tubes. Anyways, so in here we have three 12BY7s, which is kind of neat. So 12BY7s are video output tubes in early televisions. So there's lots of these things around. It's a relatively high transconductance type tube. They were used a lot in amateur radio gear, like ham radios. These would drive the finals, so they used these as a driver tube. So they worked very well for that. There's lots of them around, so why not use them in other application? A 0A2 is a shunt type regulator, so these can be used as a reference as well, depending on how they have this set up. The schematics for this are very available. I don't have it printed off or haven't looked at it at this point, but I will get to that. I'll go find one and we'll take a look at the schematic together. 6AU6 is a sharp cutoff type pentode tube, so used in RF and IF amplifiers and radio receivers, another very common tube. In fact, these are all really common aside from maybe the 6BW4s. So those aren't all that common. The 6BW4 is a rectifier tube, so it's a full wave rectifier. Now, the 6BW4, it's kind of interesting to have two of them in here. It's we'll have to take a look at their arrangement and see what they're doing. But a 6BW4 is a really small package tube that can deliver a lot of current. So interesting that they're using two of those. A 6BQ7 is a tuner tube. You find these a lot in early radio receivers and FM radios, and you'll find these a lot in the tuners of televisions. Now, the 6BQ7 is a great tube. I guess you could look at it something like a 6DJ8 kind of thing, an early 6DJ8, or possibly an early Decision, maybe before the 6DJ8 was used a whole lot. But anyways, the 6BQ7 is a great tube. The only problem is they were very known for developing heater to cathode shorts. So you get ripple on the cathode, and then of course it would introduce hum, and if it's in a television, it would cause picture issues and all sorts of things, because technically you're hum modulating a cathode, right? Now, same thing with radio receivers. So the 6BQ7 really known for HK shorts, but the rest of them are, relatively good. It'd be actually kind of interesting to know, come time to maybe actually go and fully restore this thing, we'll take a look at all the tubes and see if there are any HK shorts. Filter capacitors, most likely. More caps up here. Power transformer, nice big power transformer for this thing, and that's really kind of cute. Tektronix actually punched a hole in the side so you could see their symbol and the part number on the transformer end cap or end bell. So that's kind of cute. All right, let's take a look at the other side. I don't think I can analyze any more on this side. All right, so I'll just turn this over, and I'll have this up like so, because these things don't like to release that well when they're laying down, I find. Look at that. Put this over here. Look at that construction. Does it get any nicer than that, really? Like, I mean, you look at this for point-to-point wiring. Does it get any nicer than that? The nice ceramic strips here, and the way they've joined everything here. Now, in the early Tektronix oscilloscopes, they had silver solder inside, because they used silver solder on these to stop any problems with these little connections here separating from the ceramic strip. Let's put it that way to keep things simple, all right? So if you're ever working on a piece of Tektronix gear, using regular solder once or twice might be okay, but if you're repetitively heating something like this and removing components, what ends up happening is, since this is silver solder and you have regular solder or just whatever type of solder that maybe doesn't have silver in it, what'll happen is the silver will migrate towards the heated element, or the heated tip of your iron, and what that does is that causes separation. So you always want to use a silver solder when you're servicing these things. Now, if I remember correctly, it was about 3% silver, I believe, way back when. Nowadays, the common silver solder is about 2%. That's still fine. Just a standard nowadays 2% silver solder would be fine for this. If you want to search for the 3%, you're just getting picky at that point. So that is fine. Again, you can get away with using regular solder. You one repair or something like that, and after that you want to start using the silver solder again. Standard Allen Bradley style resistors. So these are 2 watt Allen Bradley resistors here. We have 1 watt Allen Bradley resistors, and then we have half watt Allen Bradley resistors over here. We have some capacitors in parallel. Just very nice design, very clean. Ceramic capacitors over here. Some nice resistors up in here as well. So yeah, just very well put together. I'll zoom in on this just a little bit more so you can take a look. Nice little Allen Bradley control right there, AB on it. So the nice thing about these particular Allen Bradley resistors right here is they weren't as susceptible to moisture ingression as the roundies were. I mention this a lot when I'm working on radio. So when you see the ones with the squared off ends like this, they're usually pretty good. They hold their value. But if they're rounded on the edges and it's been in a garage or in some type of a moist environment, a lot of the times the moisture ingression causes the values to move around. So, this one's 180 ohms, it looks like, at 10% here. This one looks like 270 ohms at 10%. So they're, all just really standard values. 2.2k ohms right here, all 10%. 47k ohms with a little capacitor across it here. 150k ohms right here. 3.3k ohms right here. 220 ohms right here. Just standard stuff. This one here is 1.2k ohms. So, yeah, pretty much just all standard standard values in this thing. Very nicely constructed. Nice little shield on that tube right there. So they have obviously done their homework when they put this together, and I would expect nothing less from Tektronix. Look at the way they've wire loomed everything together here. They're using some form of a plastic loom. They're not using any thread like they used to in the old radios. Very nice. Probably a nylon or something like that. Again, just fantastic construction. Okay, let me go dig up a schematic for this thing, and let's take a look at the schematic and see what they're actually doing in this thing. Schematic found. All right, let's take a look at this. So, first of all, the 6BW4 tubes are actually 2 full-wave rectifiers, and what they've done is they're using one entire tube at one end of the winding and one entire tube at the other. So they're just tying the plates together to just allow for more current delivering ability. And they have a 125 microfarad capacitor right on the cathodes there. So that's a lot of filtering. So they obviously want a very nice clean supply. So what they're doing is they're using this so they can put a very large filter capacitor here and get quite a bit of ripple reduction here. So I've gone through explaining the way filter capacitors work on this channel here, and I explained it in a very extremely simple way. And I also have on Patreon, I have another example showing actually how diodes switch and things like that on Patreon as well, using LEDs in a bridge rectifier and all that, so to make things all that much more simple to understand. So I've gone through an explanation here, and there's also an in-depth one up on Patreon if you're interested in that as well. So the 0A2 is just a shunt regulator here. So they have a shunt regulator, and this is the dropping resistor here. So they're taking this 240 volt line, and of course this is a 150 volt regulator, so we get 150 volts here. So shunt regulators are great. Yeah, there's just a slight bit of movement here depending on the tube, but relatively well regulated at that point. So it's a gas type regulator. And we have all of our different voltage taps here. So it looks like from what I can see on my monitor screen here, 120. I'll just zoom into this a little more. So 120, 180, 200, and 225 looks like what's happening there. Here's the 6BQ7. So they're using it as a multi-vibrator is what they're doing, and this is what's making our square waves. So we have our square wave coming off the cathode here and running into this 12BY7, which these would be used just as pulse shapers. All right, so what they would do with this tube is they're basically causing the tube to conduct heavily, and then they're taking the grid into cutoff. And what they're doing is they're just basically trying to shape a pulse. It's a pulse shaper tube. And then by the time we get to here, we're dealing with a pretty nice looking square wave, and then this provides the drive at the output jack that gives us our very nice square wave. Of course, we wouldn't want anything like this, right? You can see the overshoot on the downward direction here. You can see overshoot on the upward direction over here. We don't want that if we have a square wave, right? We want a nice clean square wave, and that's what they're accomplishing through this pulse shaping network. So they're using those 312BY7s for that. Kind of neat. And then the 6AU6 would just be a driver which drives the output. And then what they're doing is, so they're varying the screen voltage here. So you can see that we have a 50K potentiometer right here, and then that runs to the screen grid of the 6AU6 tube. So the first grid you see is the control grid, the second grid is the screen grid, and the third grid is a suppressor grid, and then this is the plate right here. So whenever you're looking at a tube, that's the order: control, screen, suppressor. All right, and that's what it is. Whenever you have a tube that just has one grid in it, that's just classified as a control grid. So this is a triode, and these are pentodes over here. Okay, pent meaning 5, and triode meaning 3, right? And of course, we have a dual diode here. So the 6BW4 is, you could basically picture 2 diodes right here. Right? That's all basically the 6BW4 is just a dual diode. Now, if they didn't need as much current delivery, what they could have done is just had one of these tubes, but one plate would go to this end of the winding and the other plate would go to this end of the winding, and then the cathode would run out. But again, chances are if they did that, right, you can't really have a whole lot of capacitance. You have to be careful with the capacitance on the cathode of vacuum tubes. Reason being is there's a small bonding wire or connection wire, you could say, from the lead out pin on the bottom of the tube to the actual cathode. And if you put too large of a capacitance here, of course, if the tube is already warm, say you cut the power, and then turn the power immediately back on, it has to charge this capacitor right away and also furnish all the current to the rest of the circuit. And what that'll end up doing is blow that little bonding wire from the actual cathode to the lead out pin inside the tube. It'll blow it right off. It actually acts as a fuse. So you need to be very careful, and obviously they've done a lot of experimentation, probably cycled this thing on and off at a rate to where the power, all of the tubes in here would drain off all the filter capacitors and then turn it back on while the tube cathode is still glowing, while it's still basically trying to be in emission. You could look at it like that. And that puts a very heavy surge on the actual tube. The tube is dealing with, again, charging this from pretty much an empty state and all the rest of the capacitors, and it also has to feed the entire circuit. So by putting two of these in here, you get more current delivering ability, and of course, you can have that larger capacitor here, which of course, more capacitance in this case is going to give us better filtering, right? So you can see over here, because we have a dropping resistor here, this is the dropping resistor for this. Since this is a shunt type regulator, you can't attach this directly to this, because what this is going to do is it's going to try and clamp this with all its current down at 150 volts, and what that's going to end up doing is burning this out, and then of course burning out the 0A2. So we have a dropping resistor, again, because this is a shunt regulator. So this is the part that gets warm right here. And then, of course, we have our supply out here. We have a 220 ohm resistor right here and another 40 microfarad to make things nice and stable and to even provide a little bit more filtering. You can see, like, they have lots of filtering here. So we have the first filter right off the cathodes at 125. We go through a small resistor here, another 125 here, another resistor, 40, another resistor, and 40 over here. We have another 40 up here. So there's capacitors everywhere in here. So yeah, definitely that's the reason that they're doing this, so that they have the current delivering ability. These are filament windings for the tubes. So they have separate filament windings for different types of tubes. They have two windings in here. It looks as if they've done this so that they can run this off of different voltages. So you can have run this off of different taps and things like that. What else can I tell you about this here? Trigger, which would run to the scope's trigger input, if you wanted to use that option. So all the cathodes tied directly to ground, as you can see this here. It's a nice little network here for doing the shaping. You can even see, if you look here, you can even see some shaping already happening just through this little network right here. You can see this, right? It's actually looking pretty good all the way from this with this massive overshoot here. It's actually pretty good, but once it runs through this, again, we start to get that now on the bottom side. And then again, it starts to look a little bit better here. So you see a little bit of overshoot here. And then by the time we get up here, it's starting to look really nice. And then we have our drive furnished by this tube, which is driving this 52 ohm output we have right here. And then we have a nice square wave. So really nice. Again, varying the screen voltage allows you to basically turn this tube on and off. It's like having a dual gate FET, okay? You can look at the 6AU6 in this application kind of like a dual gate FET. So the signal would be in one gate of the FET, and the other gate of the dual gate FET would be attached to a VR like this. By turning on that second gate on and off, or basically applying positive voltage to it or bringing it close to zero, you can vary how the how the FET's operating. So you can basically shut the thing down or turn it on, so you can vary the amplitude of the square wave over here by doing that. Basically, you're turning the tube on and off by doing that. Or in the case of a FET. Compensation networks and stuff. They thought of everything. They did a really, really nice job. Okay, so enough analyzing this schematic right here. I'm going to attach this thing to a power supply and let's see if we can bring it to life. Will it come to life or will it make smoke? Place your bets now. All right, I'm about to turn on the current limited isolation transformer and variac supply. So the switch on the front is on, and let's see if we can see any action here. So here we go. The variac is at its maximum, so it should probably, through the bulbs, be delivered about 75 volts or something like that. And if anything goes wrong, the bulbs will just light up. So here we go. See the fans spinning nice and slow. And it's coming up slowly. That is a very quiet and well-balanced fan. At least at the reduced line voltage, at any rate. I'm not seeing any glowing cathodes here yet. Let's see, is anything glowing? Can we see anything? Tubes are looking pretty dark. I'll just let this sit like this for a while. Oh, I think I see some tube filament reflections on the bottom there. You see that right there? Let's see if this is happening. Hard to see these tubes in here. Oh, yeah, I see the filament lighting up there in the 12BY7. The tubes are lighting up, so this is a good sign. Okay, so what I'm going to do is I'm going to let this run at this reduced voltage for a while. The bulbs are about half lit, so it's about right for something that's going to draw that amount of current through this transformer right here. So I'm going to let this sit for about 10 minutes, and I will be back in 10 minutes, and then we'll apply full power. I just want to make sure that I let the capacitors come up nice and easy like. Okay, 10 minutes has passed, or longer. So here we go. I am going to bypass the bulbs and give it full line. Here we go. So the fan is a little noisier now. It's lighting up. So you can see how this regulator tube glows kind of a powdery blue color. That's normal for 0A2 tubes. Some of them will glow orange as well, just depending on the gas. This is very common for this tube. So if you see a tube in a receiver that says 0A2 and it's glowing a blue color, it's not gassy, all right? Because gassy tubes will glow a powder blue color. It's actually supposed to do that. That catches a lot of people. In fact, I had a call from a friend not long ago saying, hey, I've got a tube that's glowing a powder blue color. I think it might be bad. Do you have a replacement for this tube? And then he gave me the number, and it was like an OA2 or something like that. So I remember saying, no, that's supposed to do that. And he's like, oh, okay, thank you. I saved him some money, right? He was going to purchase another tube. He would have found out that it glows powder blue as well. So everything's glowing nice. All the tubes are glowing real good. Now what I'm going to do is I'm going to go get an oscilloscope. So I'll just shut this down so I'm not worried about moving this. I'm going to go get an oscilloscope and I'm going to turn this back on and we'll see if it's going to make our actual square waves. So you can see it says here square wave generator. 3 millimicroseconds rise time is what it's rated at. So this is old speak. This is the way they used to write things. So 1 gigahertz would be 1 kilomegacycle. That's how they would say 1 gigahertz way back in the day. So if you had a 3 gigahertz signal, it would be 3 kilomegacycles. All right. So 3 millimicroseconds, if you were to have 1 millimicrosecond, that would be 1/1000th of a microsecond, which in today's speak is 1 nanosecond. So what's this going to be? This will be a 3 nanosecond rise time. I have the signal generator attached to my oscilloscope here. So I have a coax output here, 50 ohm coax, running into this little T-type connection here. There's a 50 ohm termination here because this is a 1 mega ohm input scope. So it needs to have the correct termination. And let's see if we can fall within the 3 millimicrosecond rating. So we want to come in on a rise time less than 3 nanoseconds. Okay, so I'll turn this on. Let's see what we have going on here. Okay, so it's on auto there, so that should make things nice and easy. So what I'll do is I'll zoom in to the screen here a little more. Try and get the settings in there, so if I poke at any of the buttons here, you can see what's going on. I'll just move the focus up to the screen. Okay, here we go. I'm going to turn on the square wave generator now. Power on. I have this power off too. Let's turn that one on. So are we going to get anything? Let's see. Oh, it's doing something. Hey. It's making square waves. It's working still. To tell you the truth, it's a piece of Tektronix equipment. I'm not surprised. So it's right at 1.159 megahertz right now. So that's its max frequency. So we'll just turn it down to the minimum here and see what it says. Its minimum frequency is 160.5 kilohertz. And right about center, what's that going to give us, about 500 or something? Yeah, 533 kilohertz, or 0.533 megahertz. That's a roughly centered. I'll probably just breathe on this and it'll move that around. So right at 500 would be right there. And yeah, that's still very close to center. So the amplitude is really high. Turn that right down. So the amplitude is going to vary on this from 0.3 of a volt peak to 3 volts peak. I believe that exceeds what the device is supposed to actually do, but you know, it hasn't had a cal or anything, so I'm not expecting it to be perfect, right? All right, so I'll just leave everything where it is right now. So now what we want to do is we want to find out the rise time. So let's see if it falls within the 3 millimicrosecond range. So that would be the worst case scenario, right? So I'll go reading 1, and I'm going to go over to rise time. Drum roll, please. So here we go. Okay, so I'll get rid of this. Now what I got to do is move this so we can take a look at one of the edges here. Okay, so you can see it's on this edge right here. So what I'm going to do is expand this until we get to that 2.6 nanoseconds. We're in under 3. So it's still falling within spec that way, and that is one of the most important specs. So it's still under 3 nanoseconds. Not bad, Tektronix. So this little unit is still working well. So there you have it. Old piece of Tektronix gear from 1959, and it's still working very well with what looks to be almost all the original components. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid-state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. If you want to be notified as soon as I post a new video, don't forget to tap the bell symbol. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.